Thank you very much. Well, okay. I wanted to chat about kind of a bunch of new things that have emerged in the last about 5 years or so that frankly surprised me a lot. I did not think we were going to figure out lots of the things that we figured out, but it's really exciting that we have. And I want to tell you a little bit about that. I should probably go back to kind of the beginnings of this journey, which for me was at the beginning of the 1980s. And I was interested at that time. I had been doing particle physics and things like this. And I got interested in kind of how does complexity arise in the natural world? And so theory number one, use all the fancy mathematical physics I knew to figure that out. That really didn't work. So I kind of went to theory number two, which was to think about sort of what does one foundationally think about when one is thinking of making models of things. And the question is what raw material should you make models out of? And what I kind of realized is that in making traditional mathematical models, we think about differential equations and calculus and all these kinds of structures. But if we just go to sort of the basics, what we're interested in is we have certain rules by which a system operates. We just want to run those rules and see what happens. So I got interested in, well, what's out there in the sort of computational universe of possible rules, a field that I would now call ruleology, the study of simple rules and what they do. So let's just look at some of the very early experiments that I started doing. I particularly started studying these systems called cellular automata, which have the feature that they are very easy to visualize. And so here's the basic setup for a cellular automaton. You have, let's say, a line of cells. Each one is either black or white. And then it's a dynamic system. So in a sequence of steps, the color of each cell is updated according to the color of the cell above it and the cells to its left and right. Okay, so that's kind of the setup. And now we can say, well, if we follow that rule, what does the system actually do? And we might think to ourselves, yes, this is a very simple rule, so the system will do something very simple. And indeed, we will validate that our intuition about that is correct, that with this very simple rule, the behavior of the system is very simple. Okay, let's say we try a slightly different rule. Let's say we try a rule like this. Let's run that rule. Here's the result. Okay, so everybody can guess this is a nice fractal-like structure. We run it a bit longer. We see that, well, yes, the pattern that's generated is very intricate, but nevertheless, it somehow reveals the simplicity of the underlying rule through its regularity. So you might then think, okay, that must be a general result, that for any rule this simple, that the simplicity of the rule must shine through in kind of the behavior of the system. But then, well, you can sort of turn your computational telescope out into the computational universe and find out what actually happens. So this is an experiment I first did in the beginning of the 1980s. It's a lot easier now with Wolfram language and so on. But this is what we're doing. We're looking at all possible rules. There are 256 possible rules with these 8 possible outcomes here. And we're looking at all of those rules and we're asking, starting just from a single black cell, what do these rules do? So many of them do very simple things. We can keep scrolling through. We'll find some nested fractal patterns and so on. And we keep going, we keep going. Okay, this is my all-time favorite science discovery. This is rule 30 in this sequence of possible rules. And let's take a look at what it does. So let's look at rule 30. Here's the rule. And then let's just look at what that rule actually does. So we can say, here's 40 steps, and let's run 400 steps. So this is what that does. So this is very surprising because a very simple rule, and yet even starting from this very simple initial condition, there was no kind of sensitive dependence on initial conditions, excavation of detailed, many digits of the initial conditions or anything like that. This was just a very simple rule, very simple initial condition, and yet this is the behavior we get. There's a certain amount of regularity that you can see over on the left-hand side here. But for example, if you look at the center column of cells in this pattern, it is, for practical purposes, completely random. In fact, it's random enough that we were able to use it as a pseudorandom generator in Wolfram language for many, many, many years. It's been replaced now with something slightly more efficient using the same general ideas. Um, but when I first discovered this in the early 1980s, I interacted a whole bunch with lots of mathematicians. I happened to work at the Institute for Advanced Study in Princeton at that time, and uh, uh, for example, a friend of mine named Jack Milner was a mathematician who got really interested in this. And he's like, we're going to solve this. This is it's a sufficiently simple setup that it's going to be possible to kind of crack this system mathematically. That's what I assumed as well. So we try all kinds of methods from statistics, cryptanalysis, dynamical systems theory, computation theory, and so on, and none of them worked. And so and if you wanted to ask a question like, okay, let's find an exact solution for what this system does. Let's figure out after t steps where t could be a trillion or whatever else, what will the color of the cell in the center column be? Uh, One just couldn't find any way to figure that out. So what one might think, well, that's a failure from a mathematics point of view. But what I kind of realized is actually that failure is sort of the most interesting thing that one can say about what's going on in a system like this. And the way to think about it is there's a phenomenon I call computational irreducibility. That's the thing that's happening here. And we're used to lots of kinds of systems in physics, for example, like, I don't know, an idealized two-body problem where you have an idealized planet orbiting an idealized star, and if you say where's the planet going to be, a million revolutions in the future, you don't have to follow all those revolutions. You can simply use a formula, fill in the number, and get the result. And that's sort of the thing we've come to expect as kind of a success in mathematical physics and so on, is to sort of jump ahead and make those predictions. But what happens in systems like this, it seems, is that they are instead computationally irreducible. Yes, you can figure out what will happen a billion steps in the future by running each step and seeing what happens, but there's no faster way to get to that answer. So how should we think about this fact? So I think the way to think about it is to think of a system like Rule 30, like this cellular automaton, as doing a computation. And the question then is, how sophisticated is that computation? So we can think of ourselves making a prediction about what's going to happen in the system as also doing a computation. And so, in a sense, by assuming computational reducibility, we're saying the computation we can do is somehow fundamentally more sophisticated than the computation that Rule 30 itself can do. Well, it seems that that isn't how things work. And in fact, we got kind of a precursor of that back in the 1930s when universal computation was discovered. It had been assumed before that time that, if you wanted to make, get a machine that computed square roots or something, you get one piece of hardware. You want to get a machine that computes squares or something, you get another piece of hardware. But the thing that became clear, well, first in 1920, then in the 1930s, was that actually, no, it's possible to have a single universal machine which can do any computation that you specify for it to do by giving giving appropriate initial conditions. So that gave the idea that yes, it is possible to have a system which can do a computation, sort of be arbitrarily sophisticated in the computations it can do. What was completely not obvious at that time was how ubiquitous that phenomenon might be. And it was generally assumed that to make a universal computer took lots of effort. You'd had to actually build a microprocessor or whatever with lots of complicated circuitry and so on to make something which could be a universal computer. It was also kind of assumed that physics was not something that was in sort of the same world as computers and the kinds of discrete systems that computers are set up to be. So the thing that I kind of started to think about in the 1980s was, well, actually, perhaps we should think of kind of all processes in nature as computational processes. And then the big sort of empirical observation from studying the computational universe of possible programs is that it seemed that it wasn't the case that there were sort of a continuous range of possible complexities of behavior in programs. Instead, what seemed to be the case is that above some pretty low threshold, kind of all of these different programs, even very simple ones like Rule 30, were kind of equivalent in the sophistication of computations that they could do. And that led to this thing that I call the principle of computational equivalence, which basically says that as soon as the behavior of a system is not, in some sense, obviously simple, it will turn out to be equivalent in the sophistication of computations that it is doing. And there's a principle that we've got progressive pieces of evidence for. It's a principle that has been a very useful guiding principle. It's at some level, it's the kind of thing that in some sense you can prove, in some sense it becomes a definition, in some sense it's a fact about the world that we live in. So it has sort of a slightly complicated epistemological status. But the thing that's been interesting over the years is progressive evidence for the principle of computational equivalence. Okay, so what does the principle of computational equivalence imply in a case like Rule 30? It means that the things that that we can set up to kind of jump ahead of Rule 30 are computationally equivalent to Rule 30 itself. So that's kind of why we can't expect to kind of jump ahead of the actual evolution of Rule 30. It's because the apparatus that we have to do that jumping ahead has the same level of computational sophistication as Rule 30 itself. And so we're kind of stuck just having to follow what Rule 30 is doing, and we're stuck with this phenomenon of computational irreducibility. So computational irreducibility has many, many consequences. It's something that is at some level sort of a limitation on what we can expect to predict, at least exactly, in science. It also has all kinds of other implications. In a very bizarre twist of history, I think it became the sort of impetus for the idea of proof of work for Bitcoin and so on, as you have to do the work to get the answer type thing. It also is something that has lots to say about questions about things like AI ethics and questions about if you build a system that is sort of doing computationally sophisticated things, then it becomes inevitable that the system can do things that you don't expect. That's sort of a consequence of this phenomenon of computational irreducibility. But computational irreducibility also has a ton of consequences in the foundations of physics and mathematics and biology and so on, which perhaps I'll talk about here. But so once you see the fact that you can get from a rule as simple as this to behavior as complicated as this, you start wondering, well, what does that mean for the natural world? And something I've studied a lot is there are all sorts of systems in nature where kind of the source of their complicated behavior is this kind of fundamental computational phenomenon connected with computational irreducibility. But another thing you might start wondering is, well, what about fundamental physics? If you can get such kind of complexity of behavior from such simple rules, what about our whole universe? Is it conceivable that our whole universe could be the result of running just some rather simple underlying rule? Well, the thing that's sort of the beginning of that story has to do with thinking about sort of what is the universe made of? And one of so there's sort of was a question that started in antiquity: is the universe made of discrete things or is it continuous? And that question wasn't answered for matter, for example, until the end of the 19th century. By the end of the 19th century, it had become clear that matter is made of discrete things, discrete molecules and atoms and so on. Then that shortly thereafter, you could think of light in the same way. Beginning of the 20th century, most physicists thought that space was discrete as well, but they could never make that work. The mathematical structure needed was never consistent with relativity. That never worked out. By the 1930s, people had sort of given up that idea and had just concluded, no, space is different. It's not like particles. It's something where space is fundamentally continuous, and we can think of things in terms of manifolds, and we can imagine just placing things anywhere we want in this background structure of space. Well, one of the things that I started wondering about in the 1990s, I guess, was whether, in fact, one could think of space as being discrete and think of that as being sort of the substrate for what the universe is made of, so to speak. And one thing that was very clear was that something like a cellular automaton was not going to work out. A cellular automaton sort of already has built in the fundamental structure of space and time as this grid of cells and so on. So the question is, well, what kind of thing might space then be made of? And so I started thinking about sort of what are the most structureless structures that you can imagine. And that led me to thinking about hypergraphs, well, initially graphs and then more recently hypergraphs. And sort of the idea is, well, what if all that there is in the universe is a collection of atoms of space, and the only thing we know about these atoms of space is that they are distinct from each other and they have certain relations to each other. So those relations can be encoded as the hyperedges of a hypergraph. And then we say, well, so the idea is that everything that exists in the universe is part of this hypergraph. And so the particles that exist, they're some kind of topological structures, topologically stable structures in this hypergraph and so on. What does this hypergraph do? The idea is that the hypergraph is being updated according to rules, a little bit like cellular automaton rules, but now these are network rewriting rules that say, for example, if you see a piece of network that looks like this, rewrite it into a piece of network that looks like that, and just keep doing that. So one of the things that you kind of, that sort of disappears at the beginning in all of this thinking is the idea that space and time are the same kind of thing, which was actually something that, well, eventually, I think it was Minkowski who kind of had the idea that, well, it's a very nice quadratic form that you get by combining space and time, so we got to think of them as the same kind of thing. That wasn't a thing that physicists had actually imagined was the case. And I think that's kind of a somewhat of a wrong turn. I think that time is really this process of the progressive kind of computation of the next states of the universe, whereas space is the extent of this hypergraph and the kind of relations between all these atoms of space. But so the question then is, well, what happens if you just start off with some hypergraph here, and this particular one is just an ordinary graph, and you keep applying these rules to it, you get these bigger and bigger graphs, and you can get all kinds of different structures with different underlying rules. Sometimes you can kind of tell what's going on. Like here's a particular rule where if you run it for a while, you get a structure like this. It kind of knits itself something that kind of looks like a two-dimensional grid. Or you can have another kind of rule here, which after you run it for a while, produces something which is actually a kind of an orbifold-like structure that has that looks like this. So the idea is, well, what if kind of everything that's in the universe is the result of the rewriting of some hypergraph, and that sort of the only thing that exists in the universe is space, and all of the particles and things like that are features of the structure of space. What can we say about that? Well, one of the big projects that we have going on right now is to build kind of the mathematical structure that one needs to understand what happens when one builds space from the limit of hypergraph rewriting. And well, let me sort of give a rough indication of the story there. There's always a question when you start off from sort of microscopic underlying system, what will the continuum limit of that system be? So a classic case, which turns out to be surprisingly related to what we're talking about here, a classic case is molecular dynamics and the second law of thermodynamics, something I've been interested in for sort of an infinite time. So in the second law, you're dealing with a bunch of, you might be talking about a bunch of discrete molecules bouncing around, and the main result is that even though you might start those molecules in some simple configuration, in the course of time, the configuration seems completely random. And you can go and trace, what do these molecules do? You can kind of simplify what happens. You can kind of try and analyze what's going on. But one of the big results from molecular dynamics is the limit of molecular dynamics is fluid mechanics. Now, it hasn't been possible to give a really rigorous derivation of that fact. Hilbert tried to do that for a decade or so at the beginning of the 20th century, and a certain amount has been done since then. I think we now have a little bit of a perspective on how that really works. But the main point is that from that discrete underlying dynamics of molecules, there emerges in the continuum limit the Navier-Stokes equations and so on. So as kind of a question you can ask is, in the case of hypergraph rewriting, what is the continuum limit of hypergraph rewriting? So it turns out, with a bunch of footnotes, mathematical footnotes that we would love to be able to really resolve in a good, rigorous way, but with a bunch of footnotes, we can say that the continuum limit of hypergraph rewriting is the Einstein equations. Just as the continuum limit of molecular dynamics is the Navier-Stokes equations, the continuum limit of hypergraph rewriting is the Einstein equations. So what we're saying is that if there is a discrete underlying hypergraph structure, then what we will observe at the scale we're observing the universe is behavior according to the Einstein equations. Well, let me just mention something about the second law of thermodynamics, because it's going to be relevant to other things that talk about. There's a question of why does the second law work? And we can sort of simplify our story about molecular dynamics. We can actually simplify it down to the point where we actually have a little cellular automaton. Actually, this cellular automaton is microscopically reversible. So in other words, for every state, there is both a unique successor state and a unique predecessor state. And we can set it up so that, like in the middle of this picture, we have a simple state. And as we evolve it forwards in time, it gets ground up into something more complicated. As we evolve it backwards in time, same thing happens because the dynamics is fundamentally reversible. But now the question is, what the second law of thermodynamics says is it will typically be the case that even if you start from a simple initial condition, the thing that you'll get will look random. We characterize that in terms of entropy. Entropy is defined to be the number of states of a system consistent with the constraints you know about that system. So so what we're asking here is, well, why is it the case that the system kind of looks random here? If we were able to trace things back exactly, we would conclude that no, this particular configuration that the system gets into in this after this number of steps, it really isn't random at all. It's a very special configuration that was the result of evolving from this very special initial condition. But the big point, I think, is that we don't get to do that because the dynamics of this underlying system is computationally irreducible. And in order for us to go back from the configuration that we've reached here, we have to do kind of an irreducible amount of computation. And the key point is that observers like us of things like gases and so on are computationally bounded. We have kind of finite minds that run at a certain speed and so on. We don't get to do the level of computation that the gas molecules are doing. We are very limited in the amount of computation we can do. And it's because of that mismatch between the amount of irreducible computation that's going on at the level of underlying molecular dynamics and the computationally bounded computations that we can do as observers of the system. It's that mismatch that leads us to the second law of thermodynamics. So in other words, it is because we are observers of the kind we are that we believe in the second law of thermodynamics. If we were observers who were computationally much more sophisticated than we are, we would just immediately say, oh, I recognize that that sequence of bits here. It's a special sequence of bits that came from that special initial condition. But it's because we are computationally bounded observers that we believe in the second law. So in other words, we are in effect deriving the second law from our nature as observers of systems. Okay, let's go back to talking about space-time and the kind of underlying structure of fundamental physics. So we've got this limit of a hypergraph, and we're trying to build what we call infergeometry, which is kind of a version of geometry. I think maybe Pavel talked about this earlier, a version of geometry that does not assume that in the end, you've got a manifold that in the end microscopically is like patches of Euclidean space, that in this system, in the end, you've got a hypergraph. And the question is, how can you rebuild all of geometry and differential geometry on that basis? So a number of things immediately don't work. For example, you can ask the question, what's the dimension of what's the effective dimension of this hypergraph that is that might be a limiting large hypergraph? Well, you can kind of estimate that by saying, let's start from a particular node in this graph, and let's just look at the kind of ball that you get by going r steps in graph distance away from that node. And what you can say is, well, we can say we're dealing with sort of the approximate dimension of the system by saying, how does that ball grow? If that ball grows like r to the d, we say that exponent d is our estimate of the effective dimension of the system. And so that you find that that means that these hypergraph systems don't necessarily have, for example, integer dimensional limits. I think this one here has a limit of about 2.6 dimensions, and so on. Well, you can, if you look at the growth rate of these geodesic balls, the leading term is r to the d. The first subleading term is proportional to the Ricci scalar curvature. And that's kind of the beginning of the story that leads one to the Einstein equations, is the fact that one can start looking at kind of things like these geodesic balls and looking at kind of their growth rates. What you have to do to deal with the space-time case is to look at essentially light cones rather than these balls in space. Actually, let's talk about the role of time in these systems, because the thing that you realize is what really matters in this system is the kind of causal graph of events in the system. So you can think every little graph rewriting is an event. It's something that affects some number of atoms of space. It transforms some set of atoms of space into other atoms of space. And you can imagine saying every one of those transformations is an event. And then you can ask, what are the causal relations between those events? In other words, a future event may require atoms of space that were produced in a previous event. So that defines a causal relation between those two events. So you can draw a causal graph that represents that collection of causal relations. It's a partially ordered, the set of events is a partially ordered set. And this causal graph is then sort of a representation of the history of this system as it progresses. So then how do you get space? Well, space, you can think of the sort of a sequence of events here. You can think of time-like curves, which are sequences of events that follow each other in this causal order. Space, so that's kind of a chain in this partially ordered set. Space corresponds to antichains. Slices of instantaneous slices of space correspond to antichains. So what one's saying is one can there are many different ways to foliate this causal graph. These will correspond to different possible reference frames for defining simultaneity surfaces in space. So we can set up these different space-like sequences of space-like hypersurfaces. Each possible space-like hypersurface defines a hypergraph that is the thing that we get by kind of threading through these events. Which events have happened by the time we reach the space-like hypersurface, and therefore what configuration of hypergraph we get. So kind of the idea is we have both an ordinary infrageometry of the space-like hypersurfaces, the hypergraphs, and we have what we can call causal infrageometry, which is the infrageometry associated with these causal graphs. And both have rich mathematical structure, which we are trying to figure out right now. But the kind of physicist level result is that the limit of what happens in these causal graphs and so on is that you get behavior that corresponds to the Einstein equations. So there are a few things I might just mention in talking about that. The Einstein equations basically relate curvature to energy density in space-time. And one might ask, well, what is energy in these systems? And it turns out there's a very simple interpretation of energy in bulk. And the interpretation is it's the flux of causal edges through space-like hypersurfaces. That's basically energy. And the momentum is the flux of causal edges through time-like hypersurfaces. As you change your frame, you transform energy and momentum. It kind of explains this picture of what's going on, finally explains something that's been kind of mysterious in physics, which is why the Lorentz transformations on position and time are the same as the Lorentz transformations on energy momentum. That's just something that falls out of thinking about things in this kind of way. Well, you can study lots of things about the structure of these causal graphs, hypergraphs, and so on. There are a lot of interesting things that have implications for physics. For example, this fact that things are not fixed dimensional means that there are potentially observable consequences of these models that have to do with dimension fluctuations in space-time that are independent of knowing the kind of discreteness scale of space-time. See, people were really lucky at the end of the 19th century that molecules were big enough that you could see things like Brownian motion through microscopes. It's not obvious whether the discreteness scale of space is big enough, so to speak, that there are any experiments we can do in the foreseeable future that will directly observe it. So finding things like dimension fluctuations, which are independent of that scale, is important. There may also be, with cleverness, so to speak, ways that one can find sort of the analog of Brownian motion for the discreteness of space. I will say one of the things that I kind of suspect is the following. You might ask, what is the macroscopic manifestation of the microscopic structure of matter as molecules? And the macroscopic manifestation, the most obvious one, is heat. People thought in the 1800s that heat was this thing that flowed from one material to another. What flows from one thing to another? Oh, it must be a fluid. Hence, they invented caloric fluid and so on. But it turned out that what heat actually is a macroscopic manifestation of the microscopic structure of matter. And so a question you can ask is there a similar macroscopic manifestation of the microscopic structure of space-time? And I have a slight guess that dark matter may turn out to be the macroscopic manifestation of the microscopic structure of space-time. So implying that it's a very poorly named thing because it's not really matter at all. But in any case, so that's a little bit on kind of the structure of space-time and so on. There's much more to say about that. But I mean, just to give an idea, this is, I think, let's see, run this. This might be, this works. Oh, how odd. Well, I thought I might be able to show you a little tiny version of the beginning of the universe, but I'm not in luck there. Okay, so the thing, what we were talking about here was these causal graphs of events happening in sort of the history of the universe. One of the things that's important about the rewriting of hypergraphs is that it's not unique. We have some rule that says whenever you see a piece of hypergraph that looks like this, rewrite it into a piece of hypergraph that looks like that. But there may be many possible ways to do that rewriting. And so, in fact, there isn't really a unique history for this hypergraph. Instead, we can draw what we can call a multi-way graph that shows sort of all the possible histories that this hypergraph can have with all the possible rewritings that can go on. Well, multi-way graphs are something which I have to say I started thinking about in the 1990s and didn't take that seriously, but I've realized that multi-way graphs just show up all over the place. They're a very good way to think about systems that one often thinks about in statistical physics, where in statistical physics you're just saying, I've got this ensemble of possibilities, but the multi-way graph is kind of representing the full dynamics of all possibilities. It's also the kind of thing that you get in like a game graph of the sequence of the set of all possible moves in a game. It's many kinds of things where they're usually analyzed in terms of, in probabilistic terms, you can think of in terms of multi-way graphs. But for our purposes here, we're thinking of the whole universe, and we're thinking about kind of the progression of the universe in these many different threads of history corresponding to all the different possible rewritings that can occur. Very simple example of that, we can rewrite strings, A's and B's and so on, and each we're saying we follow, we have some rule that can rewrite AB to either AA or ABB and so on. We can follow through this multi-way graph of possible rewritings. Well, the big thing to realize is that this story of there are many possible rewriting paths turns out to be the story of quantum mechanics in our models. And quantum mechanics becomes something that in our models is not something that you have to kind of wheel in from the outside. It's something that inevitably must be there. And in a sense, the sort of the key difference that one knows about sort of between classical physics and quantum physics. In classical physics, definite things always happen. You know, the ball follows a definite trajectory. Whereas in quantum mechanics, the idea is that there are many paths that are followed, and we only get to work out probabilities of different outcomes. Well, in multi-way graphs, the thing you can say is, well, time is progressing down here, and we're just applying these rewrites. There's kind of an analog of space, which is what we get, the sort of the transversals to this dynamics, and we can make what we call branchial graphs. And so these branchial graphs are we take a slice at a particular level here, and we ask of the states that we get at this level, how are they related by common ancestry? And we make a graph showing the relation of the states by common ancestry. And then we say, well, what's the limit of this? It's what we call branchial space. I have to say, this is a mathematically unsatisfactory situation because we really don't know what that limiting thing is like. In the case of hypergraphs, there are certain cases where we can see that the limit is like a manifold. In this case, it's really not clear what the limit is like. There's some indication it's like a Hilbert space, but we don't really know that, and it's kind of a thing we'd really like. We want mathematical help in figuring this out. And so, but multi-way graphs, this kind of slice across the multi-way graph is the representation of kind of the possible states of the universe at a certain time. The interpretation in quantum mechanics, this is a map of quantum entanglements. And what this is telling us is that there is sort of this space of possible quantum states. And so what we end up with when we think about our hypergraph, we are thinking about this multi-way graph of hypergraphs. Within each hypergraph, we are thinking about sort of physical space being laid out. And between the different hypergraphs, between the different parts of the multi-way graph, we're thinking about the different paths of quantum mechanics. Now, in fact, it's a more complicated situation because there is what we can call a multi-way causal graph, which tells us about events that are update events, and those update events can be update events that are space-like separated. They're things in the same branch of history, but they are separated spatially in the hypergraph, or they are branch-like separated events, which could be in places that are corresponding parts of physical space, but are in different branches of history. So this object, the multi-way causal graph, is kind of the big mathematical object that we want to be able to study. And by the way, what we can see is that what we're seeing is that kind of one projection of the multi-way causal graph is space-time, ordinary physical space. Another projection is branchial space. We're pretty sure that that correspondence of different projections of the multi-way causal graph is the story of kind of the holographic principle that people have talked about for the last few decades in quantum field theory and general relativity. The projection in the kind of the spatial direction, in the space-like direction, is the ADS side, and the projection in the branchial direction is the CFT side. Well, what we can at least roughly do is to say, well, what is the continuum limit in branchial space? In physical space, we can say the continuum limit is like the Einstein equations. The question is, what is the continuum limit in branchial space? We don't entirely know. There is a pretty good indication that the interpretation of distance in branchial space is quantum phase. And that when we say what, in a hypergraph, the interpretation of graph distance is physical distance. In the multi-way graph, in this branchial slice of the multi-way graph, we think the interpretation of distance is quantum phase. And so one of the things to realize then is if we think about the implication of the Einstein equations in physical space, they're saying that the presence of energy momentum, which we interpret as the presence of essentially updating events, the presence of causal edges slicing through space-like hypersurfaces, the presence of these updating events deflects geodesics in physical space. We're saying that, and that's sort of a version of the Einstein equations. That's kind of the underlying source of the phenomenon of gravity and so on. So energy momentum deflects geodesics in physical space. Well, it turns out, it seems that, again, many footnotes to be filled in, that there's a corresponding result in branchial space, that the presence of energy momentum deflects essentially geodesics in branchial space. But that deflection is now not sort of motion in physical space. Instead, it's change of quantum phase. And so what does that mean? That the presence of energy momentum is changing quantum phase. Well, the Feynman path integral is it says the phase of something is proportional to e to the I. The phase is proportional to the action. The action is essentially a relativistically invariant integral of energy density. So what this is saying, sort of long story short, what it's saying in our models is that quantum mechanics is the direct analog of the Einstein equations, that the path integral is basically the analog of the Einstein equations, but played out in branchial space rather than in physical space. So it's rather a lovely thing, which, as I say, we need lots of mathematical help to really tie down all of the pieces of this. But that, I think, is the intuitive picture, is that the Einstein equations and the path integral are the same thing, but played out in different kinds of space. Well, let's see. I could tell you about a few other things, and one thing that's perhaps an interesting direction here is you might ask, okay, so we might be able to have some simple underlying rule from which we can derive physics, from which we can derive general relativity, we can derive quantum mechanics. That's a remarkable thing. Even the idea that you could have some very simple underlying rule from which you derive all of the sort of richness in physics is remarkable. But then one might start asking, well, why did we get, with our universe, why did we get rule number 3712 or something? Why didn't we get some other rule? Well, it turns out that what I think is the case is that in some sense, every possible rule is being used. So just as I mentioned that the story of quantum mechanics is a story of all possible rewrites consistent with a particular rule being done on this hypergraph, so I think the final story is that all possible rewrites associated with all possible rules are being done. What do you get when you do that? It's like saying, imagine we have, here's a Turing machine with one particular rule, and we imagine this is a multi-way Turing machine that can use different rules at a particular step. We could then start asking, well, if we just use all possible Turing machines, we just run all possible Turing machines in all possible ways, what do we get? We get this object that in the end, the limit of that is kind of the entangled limit of all possible computational processes. And it's this thing that I call the Roolead. And it's sort of an interesting object that for some reason nobody had thought about, including me, before it sort of arose from our physics project. It's an interesting and unique object. It is, once you have the idea of computation, it is an inevitable and necessary object. You can have different bases for it. You can have a basis in terms of hypergraph rewriting. You can have a basis in terms of Turing machines and so on. Ultimately, all these versions of the Roolead are equivalent. And so the Roolead is this unique object that is the entangled limit of all possible computations. So now the question is, let's imagine that's everything there is. Well, what would we think is going on in the universe if that's how things were working? Well, we have to be observers embedded within this Roolead. And so then we have to ask the question, what do observers embedded within the Roolead think about what's going on in the Roolead? And it turns out the critical thing to determine that is, what are those observers like? And it then turns out that if we assume two things about what those observers are like, first, that we are computationally bounded, and second, that we believe we are persistent in time, with those two assumptions about observers, it becomes inevitable that observers like those must conclude certain kinds of things about what's going on in the Roolead. And the very interesting thing, and again, there are many details to be filled in, but the basic conclusion seems to be that observers with those characteristics must inevitably believe the second law of thermodynamics, general relativity, and quantum mechanics. So in other words, it becomes, once you have the concept of the Rulliad, it becomes inevitable that for observers like us, the laws of physics must be the way they are. I certainly thought, from a sort of philosophical point of view, I absolutely did not see this coming, that it will be possible to have something where you can derive the laws of physics from our characteristics as observers. But that's the way it seems to be coming out. So, okay, so that's a bit about the story of physics. Let me quickly talk about mathematics and biology and the way in which the sort of paradigm we've been building here relates to those areas. So let's talk about mathematics. So a very kind of idealized view of mathematics is you've got a bunch of axioms, and the axioms define equivalences between expressions, let's say. Well, given that, you can start building up kind of a network of equivalences between expressions, and then a theorem which says, for example, that expression at the top is equal to that expression at the bottom there. A theorem becomes the existence of a path between 2 points in this graph, and a proof is the path you took in that graph. And so then you can start asking, well, what does mathematics look like? What is, for example, one question you might ask is, what is the continuum limit of mathematics? What's the infinite time limit of mathematics? In the literature of mathematics as it exists today, there are 3 or 4 million theorems that people have written down. But what will be the limit of mathematics when the number of theorems goes to infinity? Well, you can start asking for some particular areas of mathematics, like Boolean algebra, for example. This is the beginning of the theorem network for Boolean algebra, starting from some particular set of axioms of Boolean algebra. And you can try filling this out, and you get lots and lots and lots of theorems, most of which nobody cares about. So what you find is that we humans have colonized a small part of metamathematical space. We have picked out certain theorems here that we think are interesting from this whole space of all possible theorems. And you can go and try and map out, you can pick up all the things people have done with proof assistants and so on. You can start mapping out what is the geography of metamathematical space? Where are the famous theorems of mathematics laid out in metamathematical space? And you can have some conclusions about that. But I think the thing that one really wants to think about is when one imagines mathematics kind of ground down to its axiomatic level, what is that kind of thing that one is dealing with there? It's kind of like if we imagine, it's like, are we people when one kind of is dealing with mathematics as done by mathematicians, most of it is not done at the right down at the level of the sort of atoms of mathematics. It's not done right down at the level of axioms. And in fact, it would be a big nuisance if one was doing that. This is a picture of the lemma structure to get to the Pythagorean theorem from the axioms of set theory. And it's a big mess. I think there's 7,000 lemmas used in this particular way of getting to the Pythagorean theorem. And one can say, well, if one's doing mathematics, one of the remarkable things is that one can just talk about the Pythagorean theorem. Every time you mention the Pythagorean theorem, you don't have to go and say, oh, by the way, this is our definition of real numbers. This is how everything works from an axiomatic level. You can operate in mathematics at the level of talking about things like the Pythagorean theorem. That's a remarkable fact. It's not obvious that that will be possible. It could be the case that at every turn, you have to kind of drop down to this, axiomatic level and talk about all those kinds of things. Why is it the case that mathematics can be done at this higher level? I think the story is very similar to the story of fluid mechanics. It could be the case that when you think about the dynamics of a fluid, you would always have to drop down to saying, well, this is how all the molecules are bouncing around and so on. But you don't. For most purposes, you can get away with using a kind of higher level fluid dynamics description of what's going on. And I think that phenomenon is the same as what's happening in mathematics, that essentially for mathematical observers like us, the things that we are able to talk about in mathematics can be done at a level that's kind of the fluid dynamics level of mathematics rather than the molecular dynamics level of mathematics. Now, occasionally, and that's kind of the mathematics that we've chosen to study. When you do when you look kind of at the computational universe of simple programs and so on, you're thrown into something that isn't the mathematics we've chosen to study. You don't have a choice about what happens in that world, and you're kind of thrown into issues of undecidability and so on, which operating sort of the fluid dynamics level of mathematics you don't tend to encounter. Well, there are lots of things that you can say when you start thinking about metamathematical space, and I'd love to be able to have a better geometrization of metamathematical space. We can do experiments about what it's like, but you can start making sort of analogies between the geometry of metamathematical space and the geometry of physical space. So here's an example. Here's a couple of things to say. One thing is the fact that motion is possible in physical space is not obvious. The fact that you can have a thing and move it to another place and have it still be the same thing is not obvious. It's something that you have to essentially prove is possible in a model like ours. And so now the question is, but motion happens, and particles in physical space are essentially the carriers of pure motion of physical space. An electron is still an electron even when it's in a different place. So the question is, what's the analog of motion in metamathematical space? And essentially what's happening is, at one place in this metamathematical space, you kind of are, the point of view that you have at that place in metamathematical space is the algebra point of view, let's say. In another place in metamathematical space, the point of view you have is a geometry point of view. So translation, motion in metamathematical space, is a story of translating from one kind of point of view about what's going on in mathematics to another point of view. So I think that if there is, that one can argue that there should be homogeneity in metamathematical space, and insofar as there is homogeneity in mathematical space and pure motion is possible, what one's saying is that there will inevitably be dualities between these different areas of mathematics. It will be possible to transport a thing from one area of mathematics to another. You might ask, what is the analog of the Navier-Stokes equations and so on in metamathematical space? I think a small part of the answer to that has to do with category theory, although I don't think that's the full story. But that's kind of something that is part of this sort of transportable level of mathematics. But in any case, so there's a lot I would really love to study in kind of the structure of metamathematical space and the things one could say about it. I'll just make one other comment about that. In physical space, one of the phenomena that we observe is black holes. What is a black hole? Well, in the simplest case, it's a place where time stops. The singularity at the center of a black hole, a Schwarzschild black hole, is a place where all geodesics are of finite length. Effectively, time stops. In our models, that's a much more direct thing, because what's happening is there are these rewrites of this hypergraph, and you get to a place in the black hole where there's just no other rewrite that applies. So time stops. So that a black hole is also a place where every geodesic is of finite length. There are no, time. You crash into the singularity. Time stops after there's only a finite amount of time. What's the analog of that in metamathematical space? I think the analog is black holes in physical space are the analog of decidable theories in metamathematical space. So a proof, as I mentioned before, is this path through metamathematical space. And so a question would be, well, are there, for a given theory, are there proofs of arbitrarily great length? That's, Gödel's theorem and so on tells one, and undecidability and so on tells one that in theories with undecidability, there are proofs of arbitrarily great length. So what I think is the case is that a decidable theory is one where essentially the proofs are of bounded length. And a decidable theory in metamathematical space is like a black hole in physical space. And that gets more interesting when you start thinking about the singularity theorems in physical space, where you say when there's enough energy momentum, it's inevitable that you will form a black hole. The analog of that in metamathematical space is when there's enough proof density, you will inevitably end up with a decidable theory. So that's kind of a version of that analog. Let me just mention, I think I'm going longer than I had expected, but I say a few things about biology, because it turns out the story of I should say that in mathematics, if you ask the question, what is the thing you get by looking at all possible mathematical theories? well, the thing you get is the same Rulliad object. Imagine you're looking at all possible axiom systems. You're looking at this network of theorems for all possible axiom systems. That object is another basis, is the Rulliad and another basis. So these questions about what happens in physical space and the way that observers like us parse the Rulliad to turn into physics, there's an analog of those questions for mathematics, but the underlying structure is the same structure, but we're just parsing it in a different way to get out mathematics as opposed to physics. Okay, let me talk a tiny bit about biology, and then I'd love to have a discussion after that. Got interested a while ago in sort of why does biological evolution work? And we can make a very simple model for biological evolution. It's going to turn out that there are very close analogies between sort of the story of biological evolution and the stories we've been telling in physics and in metamathematics. But let's start from something much sort of simpler. We say, let's make a minimal model for a biological organism. You can say, well, it's just like a cellular automaton. It has a genome that's just the rule of the cellular automaton. And the growth of the organism starts from this little seed here of one red cell, and it makes this whole structure, which eventually dies out. Okay, so let's imagine that we're going to mutate this underlying genome, as happens in biology. We're going to make a series of point mutations to that underlying genome. And we're going to say, let's accept those mutations when they don't make the thing that is produced from that, the organism that's produced, live a shorter time. So this is plotting the time the organism lives as a function of the mutation number here. And we're seeing that most mutations lead to organisms that live a shorter time, but occasionally there's a breakthrough and we get a longer lived organism. And if we just trace that out, we can see over the course of time, there are sort of a bunch of discoveries that get made from finding underlying rules that let the organism have some mechanism to live longer. And depending on sort of the roll of the dice about which mutations we get, we'll have sort of different discoveries about how to live longer. And it's sort of interesting to try and understand how this kind of set of discoveries builds up to allow one to get this result of living longer. But let me make an analogy. Let me ask the question, this very simple setup. We can ask, what happens with all possible mutations of the system? Well, we get a multi-ray graph, just the same as we did in the case of, I didn't explicitly mention it for mathematics, but that's the thing you're getting from applying all these different possible moves with different with axioms and so on. It's the same thing as we were getting in the physics case, and it's the same thing we're now getting in the biology case. Okay, so what we can have sort of the set of all possible mutations, but then what mutations we actually allow, the actual progression of biological time corresponds to accepting a certain set of mutations, the mutations that increase the fitness of the organism. Well, it turns out we can imagine that there's this very complicated multi-way graph of all possible mutations, but then what we're doing is we're essentially providing foliations of that graph that correspond to fitness functions which are being applied by the actual environment in actual biology. And the main result is that the fact that biological evolution works, the fact that you can go on making progress and go on getting fitter organisms, is a consequence of the fact that there is a certain computational boundedness to the foliations that the fitness functions the real fitness functions make. In other words, if the fitness function was some very, very, very complicated thing, the chances are you'd never make progress. If every organism, as soon as it was born, had to be able to, solve calculus problems or something, no organisms would survive. It's because the actual fitness functions of biology are coarse enough and computationally simple enough that it's possible for biological evolution to make progress. So in a sense, it's the environment, the fitness of the function imposed by the environment is kind of like the analog of the observer in the case of a biological system. And it is this interplay between the computational boundedness of the observer and the underlying kind of computational irreducibility, the kind of computational strength of the underlying processes that are going on that leads to the possibility of biological evolution. Now, one thing looked at very recently is, and maybe Pedro talked about this, um, is um, the following question. So, if you ask about a biological organism, um, you ask what's a biological organism made of? You know, if if you look at the innards of a biological tissue, what is it? Is it a solid? Is it a liquid? It's probably not a liquid. It's not a solid because the molecules are moving around. It's not a liquid in an ordinary sense because the molecules are not just randomly bouncing around. Instead, what seems to happen in biology is there's a kind of bulk orchestration of molecular processes. All these molecules are being sort of actively transported from one place to another and so on. And there's a whole complicated sort of story of what's happening in a biological organism. And the question is, in this thing, in this kind of bulk orchestrated matter, what can you say about bulk orchestrated matter? Is there a statistical mechanics of bulk orchestrated matter? It's like saying, you've got a microprocessor, and you could say, well, we're just going to study that with statistical mechanics. We're going to say the electrons in a microprocessor are like an electron gas, but that's a really bad model of a microprocessor. The question is, when something has been, let's say, evolved to satisfy some fitness objective, is there something one can say about kind of the structure of that system? Well, it seems that there is, and there's a whole story that recently is about a couple of months ago now, a thing I wrote about what I'm calling the rulal ensemble. So the idea is, imagine that we are trying to adaptively evolve a system for some purpose. Like, for example, we might have the purpose of having the output here be red, a big blob of red, big blue, big yellow. Well, there are different solutions to the problem of making red, blue, yellow. And here are a few of the different solutions that can be achieved by adaptive evolution, by a series of mutations to the underlying rule. So the question is, if you look at things which were the result of different possible adaptive evolution processes that all ended up satisfying that fitness function, what can you say about kind of the things that satisfy that fitness function? Or more interestingly, what can you say about the things that satisfy any computationally simple fitness function? See, in biology, you might say, well, what's the thing biology is trying to achieve in this particular situation? We don't necessarily know. But if we assume that what it is trying to achieve is something computationally simple, we can ask the question, is there something general we can say about the set of rules that are generated by if the objective is computationally simple? And the answer is, it seems that there is. It seems that in this rulal ensemble of all possible rules that have been adaptively evolved for a computationally simple purpose, all those possible rules, which are a subset of all possible rules, a tiny subset of all possible rules, that there are things one can say about rules that were adaptively evolved for a computationally simple purpose. And in particular, one of the things one can say is that one tends to observe what I call mechanoidal behavior. So these are just arbitrary random rules. But if you compare those with rules that were evolved for a particular purpose, those particular ones happen to be symmetrical as well. But if you compare those with rules that were evolved for a purpose, you find that there's a difference. What happens is rules that were evolved for a purpose, so to speak, end up with certain sort of microscopic pieces of mechanism that do not exist in rules that were just picked at random. In other words, there's a signature, even at a microscopic level, of this macroscopic fact that the system was evolved for a purpose, or was evolved for had some computationally simple fitness function. So this is kind of at the beginnings, I think, of a way to get at sort of a general theory of biology. Biology has not been an area in which there has been much in the way of theory, but this is a way in which one can potentially get at sort of a general way of thinking about sort of how biological organisms, what's in biological organisms and how are they put together. Many more things to say about that, and much that we haven't figured out. I will just mention that machine learning seems to be a very similar story to biological evolution, and the kind of question of let's see, this the question of sort of um, what's happening in machine learning turns out to be another very similar question. I mean, when we have a neural net, for example, it's quite hard to visualize what happens in a typical neural net, but you can dramatically simplify neural nets to end up, well, first with grids of connections, and then you can actually make a fully discrete analog of a neural net in which you have essentially a thing like a cellular automaton, but instead of having the same rule at every position, you have different rules at different positions, and that's kind of a discrete analog of the weights that you're picking in a neural net. Well, you can then ask, how does machine learning work in this very discrete setting? The story is very similar to the biological evolution story. As you mutate the configuration of weights, or in this case, the configuration of in this array of possible rules, you end up being able to evolve to achieve a certain purpose. And what you discover is that usually the way that purpose is achieved is something very complicated. It's kind of it's sort of a computational irreducibility story. And I think what one observes in machine learning is that within the underlying system, whether it's a neural net or one of these rule arrays or whatever, there is lots of essentially computational irreducibility. And what one is doing when one's training a machine learning system is one saying, let me take those lumps of irreducible computation and let me find a way to fit them together so that I get so that I satisfy the objectives I want of telling, pictures of cats from pictures of dogs or whatever else. And, it's again, this story of there's this underlying computational irreducibility, but the thing in that case that you're trying to achieve is something computationally quite simple, but you're using these kind of lumps of irreducible computation, fitting them together to achieve that simple purpose. So it's kind of a way to think about it is, imagine you're trying to build a wall. One way you could do that is say, well, we're going to make bricks and we're going to have this very organized, engineered wall. Another thing you could say is, I'm going to just pick up these random rocks that are lying around on the ground, and I'm going to fit them together to make this thing that serves the purpose of being a wall. It's that second thing that's happening both in machine learning and in biological evolution. In both those cases, one's kind of tapping into the kind of power of irreducible computation, and one's finding ways to sort of fit together these lumps of irreducible computation to achieve the objectives we want. Well, okay, just a little bit on, so the thing that I find remarkable is that this kind of set of paradigms that kind of emerges from thinking about things computationally seems to inform physics, foundations of physics, foundations of mathematics, foundations of biology, foundations of machine learning, and probably some other fields as well. One might ask, what is qualitatively happening? Why is this happening? Why are we being so lucky, so to speak? I think the sort of historical arc is more or less this, that a lot of these fields kind of developed in a formal way, end of the 1800s, beginning of the 20th century, things like that. And people were able to formalize things. And that led to kind of a lot of progress in all these fields. And it also led, this idea of formalization eventually led to the idea of computation. And then by the 1930s, or more clearly understood by the 1980s, one had realized that sort of formalization in bulk has certain consequences. Formalization in bulk leads to these phenomena like computational irreducibility and so on. We're now finally being able to make use of what can we do when we think about sort of formalization in bulk? What are the things that emerge from thinking about things in those ways? And I think that's why a bunch of these fields which got formalized, but then their formalization was never looked at in bulk, so to speak. And we now have methods to do that. Now, the challenge here is that we would like to connect this sort of formalization in bulk and so on in all these different fields to things where we can use kind of the methods that have been developed in mathematics and mathematical physics and so on to really kind of have more definite things to say about all these different phenomena. Now, computational irreducibility will eventually bite one, and there will be things one won't be able to say. But the whole point is fluid dynamics as possible, so to speak. There are things one can say, even though there's underlying molecular dynamics full of computational irreducibility, even though the phenomena of turbulence and fluid dynamics are probably closely related to computational irreducibility, and there are lots of things we can't say about them. But there are lots of things we can say in fluid mechanics, and we'd like to be able to say those same kinds of things about fundamental physics or about foundations of biology and so on. And that's kind of the mission that we're on right now. I suppose that I have the good or bad fortune, I one or something of having spent my life kind of alternating between developing technology and doing basic science. I've had the very nice phenomenon of being able to develop technology that provides tools that allow one to do basic science, then taking ideas from basic science and being able to put them into technology. And I've kind of iterated that about 5 times so far in my life. But one of the things that's sort of a consequence, particularly of building technology, is that a lot of what's involved there is the strategy for what to do. And I suppose I've tried to take that kind of sort of strategic thinking about what one should do to basic science as well. And kind of one of the foundational ideas of our Wolfram Institute is to take the success that we've had over the last 40 years now with our company and kind of being able to do sort of innovative R&D for technology and apply those same kinds of ideas to science. And I think it's going really well. And I think that it's interesting that we're sort of fearlessly able to attack kind of all sorts of questions in science, actually also in the philosophy of science, that have seemed quite unattainable before. I mean, a recent thing of a couple of weeks ago was attacking the P versus NP problem using kind of these kinds of ideas. And it's, I mean, the main thing that comes out of that is the realization that things are, that the sort of formulation of let's see whether, sorry, I'm just looking for this. Oh, do I not have this here? Okay, the sort of, here, I can pull it up. The main thing to realize is that the P versus NP problem is a whole story of multi-way graphs versus single-way processes. The NP is a story of multi-way graphs. Can you reach something in a multi-way graph? And you get to formulate the P versus NP question in a way that is amenable to empirical observation, empirical investigation. So one can actually show that in certain cases, if you limit the size of Turing machines that you're studying, that you can actually establish results on P versus NP and so on. And it's very very exciting that one can kind of use these methods on all of these kind of foundational kinds of questions in lots of different areas. All right, I yacked on for much longer than I expected, but I'm happy to have whatever discussion people would like here.
Okay. Can you hear me? Okay. Thank. It's not working. No. Okay. Now.
There's a lot of you. You're echoing. You're going to make me start talking about this way we have of thinking about quantum field theory and about the phenomenon we call subtime. Which is not unrelated. Okay, sorry.
Stop. Ahora.
I think you have to switch off the. Well, here, let. No, it's a problem at your end, I'm afraid.
What about now?
No.
Okay, I'm a normal person. I'm not a ghost. He can hear us, but okay. But no, but we cannot hear him. Okay, let's try. Okay, okay, try again. So you have to. What are you doing? Put the audio on. No, but you can activate it. Okay, what about now? Okay, good. Steven. Oh no, we cannot hear. ¿Qué has hecho? Está apagado el volumen. It's okay. No.
Why don't you do this? If somebody has some, why don't you switch me off, ask the question, then switch me on again?
Yeah. Ok, vamos a hacer lo siguiente. Quien tenga preguntas, que se ponga en fila ahí, iremos subiendo de uno en uno y hablará por el micrófono de allí. Vamos a ser prácticos. ¿Ok? Vale, voy a tirar esto ya. Vale. Venga.
Okay, great. Yeah, okay. Hello. Okay. Hi there. Yes, I mean, that's a very common thing. In fact, we know for cellular automata, we know an example of a rule like Rule 30. We don't know about Rule 30 in particular, but Rule 110, for example, we know can simulate any other cellular automaton rule or any Turing machine. We also know the very simplest Turing machine, a thing that I conjectured and somebody proved in 2007, that there's a very tiny Turing machine that can simulate any other Turing machine. So yes, the whole point of the principle of computational equivalence is that it is a ubiquitous phenomenon that even very simple rules can be universal and can simulate any other rule. Does that make sense?
Que quizá no oiga a través del micro, pero por los altavoces.
Okay. So we are probably implicitly assuming other things, okay? We don't really know. We would like to have a real clear axiomatic sequence where we can say exactly what we're assuming. The thing that those two assumptions are my attempt to abstract what's important about observers like us. It could very well be that there are other sets of assumptions which will also give the Einstein equations, so that observers very different from us would also observe a universe in which the Einstein equations work. My guess is, okay, so one of the challenges is, why does space appear three-dimensional to us, for example? My guess is that there are other assumptions we should be putting in, which are incredibly obvious features of us as observers, which will end up implying that the way that we parse the Roolead necessarily leads to us believing that space is three-dimensional. Because there isn't, it's not the case. I mean, even the fact that we believe in space is a complicated consequence of our scale relative to the universe. You know, if we look around, you know, in a room, we can see a few tens of meters away. Light comes to us in microseconds, but our brains process it in milliseconds. So it's reasonable for us to say there is a state of space at a particular moment of time. If our brains ran a million times faster, we wouldn't think that particularly. We would say, oh, there are a bunch of photons coming in different places, and there's no reason for us to take this sort of space-like slice of what's happening. So even our belief in the existence of space depends somewhat on our scale, I think. And I don't know what, there is probably some key assumption that we inevitably make that's really obvious to us. I mean, I'll give you, there's a whole boatload of other assumptions. So for example, another thing about us is that we're not massless. If we were massless, we would have no notion of time. In other words, if we were photons, and so we are observers who are massive observers. That's an important fact. We're observers who believe that we have a certain amount of free will about what we do. We believe that we can do arbitrary experiments. We, you know, in setting up the way we think about science, we don't think, oh, every experiment we do must have already been predetermined what that experiment will be. We imagine we can do any experiment. There are a whole bunch of assumptions that we're making about the way we are. I'm certain that in our efforts to do things like derived general relativity, we're implicitly making a bunch of other assumptions. But the two key assumptions that seem, you know, to be the most significant ones are the fact that we're computationally bounded, the fact that we have finite minds, and the fact that, surprisingly, we believe that we have persistence through time, which is completely unobvious because we're made of different atoms of space at successive moments of time. So the fact that we have this thread of experience that goes through time is something that is part of sort of our assumption about how things work. And so that's anyway. So, but it's a very interesting question. What, you know, it's sort of a philosophy meets science question of what are the things which we are implicitly assuming about ourselves and about the way that we construct scientific theories that lead us to these conclusions. And, you know, would alien minds come to the same conclusions and under what circumstances? These are very interesting questions. And I mean, to be more concrete, for example, one of the questions that I've been interested in and completely not being able to solve is when you make foliations of things, whether they're causal graphs or multi-way graphs or whatever, what is a reasonable foliation to make? In other words, how can you parameterize the computationally bounded foliations? So for example, in computer science, you might talk about we're doing a depth-first traversal of this graph, we're doing a breadth-first traversal. Those are two different kinds of foliations, but it's like what is the general way of characterizing those things? That's an example of a more mathematically defined kind of version of these kinds of questions. Interesting questions, anyway. Thanks.
Okay, let's make an experiment. Ah, it works.
Now it's working.
Okay, you hear me?
I do.
Okay, and the people hear me. Okay, great. Ahora quieres que use ese y que apague ese?
Hello. Well, I think I can hear you. Yes, I can't see you now. Yes, yeah, that works. Hi. Is what? Sorry, the that's very, by the time you've got to things like sponges, you are so far up the tower of structure in biology. I mean, but go ahead. Yes, yes. I agree. I mean, the yes, we're actively interested in that. One of the things that actually I might have mentioned this in connection with the what was just asked about observers. One of the things that surprised me is it's important to the way that we perceive the universe that there are many of us, that there are many different similar observers. That's if we want to build up an idea of objective reality, we all have to kind of be similar in what we perceive about the universe. So self-replication ends up being the fact that we can have many similar things, many similar entities, is important to kind of getting, a notion of an observer like us. But to your question about self-replication and the origin of life and so on, we're actively thinking about that right now. I'll make a few comments. I'm pretty certain that the life that we have today is not the first form of life that's ever existed. We are probably, the I don't know, the fifth, the 18th, the something or other form of life that's existed on this planet. And probably the first form was something much simpler that provided the environment that was necessary to be able to make eventually things like ribosomes, which are a very complicated machine. And so we're trying to think of what are the sort of minimal models that we can use that allow one to think about how things like life can emerge. I think one of the things that I was just recently thinking about is if some earlier form of life had actually survived on Earth, would we even know it? Because most of the assays that we have for life assume life of the kind that we have. So I think there's super interesting questions about sort of the origin of life and whether one can use these ideas to think about it. We're actively thinking about that. I don't think we yet have a really good minimal model for thinking about kind of things that can, but the real thing is that in things like these cellular automaton models of organisms, they are they don't have built into them the kind of hierarchy that seems typical in actual biological organisms, where you can have something made of molecules and then that thing that's made of a collection of molecules becomes a kind of an organelle that then forms cells and so on. Maybe we don't need that, but I think that may be necessary. And I think the similarity of code and data that exists in biological organisms in the way we were modeling biological evolution, we're assuming that. But we have to derive that if we want to derive the origin of life. So we haven't, still a work in progress, but something we're very interested in. Pedro, who I think is probably somewhere there, is a person who is, yes, there's Pedro. Hello, Pedro. Is kind of actively thinking about.
Can you
these
hear?
kinds of I unfortunately have to get going in just a few minutes here. So maybe if we have one last question, I would love to keep going for a long time, but I have to go somewhere.
Deep neural networks. No.
Well, not quite, but a couple of things. The a couple of things to say. The most, can you hear me? Yes. The uh, one thing to understand is what does it mean that neural nets work? Okay. So there are many things you can ask neural nets to do that they will completely fail to do. I mean, if you ask them to sort of trace out some computational irreducible process to compute what Rule 30 is going to do, they'll just completely fail. But the places they're successful are places where they're doing things that are like what we humans can do, like tell a picture of a cat from a picture of a dog, continue a piece of text, these kinds of things. So I think the number one thing that what's happening is that the things we are asking neural nets to do are in some sense computationally quite simple. They're not irreducible computations. They're bounded computations that our finite minds can do too. And the thing that is surprising about neural nets is that they manage to generalize and capture and model things in ways that are similar to the ways we humans do it. And I think the reason for that is that neural nets are close enough in architecture to brains that they're kind of able to do the same types of things. And I think the sort of big discovery of, for example, ChatGPT, I wrote this whole little book about this actually, is that the kind of the big thing that one realizes human language is not as complicated as we thought. There are more regularities. There's kind of, in addition to the sort of syntactic grammar of noun, verb, noun, there's also sort of a semantic grammar of what words go together with what other words. And the surprising thing is that you can just keep going with that and it makes a reasonable essay, so to speak. We didn't know that. But that's more a statement about the structure of language, I think, than it is about kind of the magic of neural nets, so to speak. I think they're only magic insofar as they're doing similar things to what we do. If you try and force them to do things like irreducible computations, they just fail. I think as a practical matter, that's why kind of the tools that we build with Wolfram language and so on, we see those tools as being kind of foundational tools for the foundational models that one can build with neural nets. I mean, another very interesting thing about neural nets is how broadly applicable they are. That a broad neural net, a neural net that is intended to do lots of things, is better than a neural net that's intended to do only very specific things. That's probably telling one something about the structure of human knowledge, and it's probably telling one sort of a global fact about that. I'll just mention one more thing, a project we're doing right now, which is an attempt to find sort of global laws of neural nets. Okay, so the question is, you've got this neural net, you know what happens at the level of individual weights and so on. There is a question, is there sort of a fluid dynamics level description of neural nets that can talk about something at a higher scale than those individual weights? So one result, this is about a week old or 2 weeks old or something, is that you can ask the question, can you tell a trained neural net from an untrained neural net? If you just throw in a bunch of weights, is there a statistical difference between a trained network and an untrained network? The answer is that there is. Now that should tell one, the fact that one can tell that statistically is the beginning of telling one that there is a sort of large-scale law of what's happening in neural nets. The question is, will that law be useful? It could be like you're doing neuroscience and you discover this amazing large-scale law of neural assemblies of neurons, and it's that they have EEG. Well, EEG is not particularly useful, so far as we know, for understanding thinking in brains. It's kind of a collective effect that is, has its interesting features, but it's not the core to thinking in the brain. And so that may be the kind of thing we'll discover in neural nets. I don't know. There's sort of an interesting question of whether there's a sort of a more global laws of neural nets. I could advertise. One of my kids happens to work on such things, and he wrote a paper recently. He won't think about it in the ways I think about it, but about discovered kind of a global result about across many different LLMs about the behavior that they show. It's a very surprising result, which I don't understand at all. I should probably wrap up here because I've got to run along. Hello, Isaac. Yes, nice to see you. Right. Okay. Bye-bye. Very nice to chat with you. I hope to meet you all in person at some point. Bye.